engineering science. So we had a little chat with Professor Bajat just before this talk, and he mentioned that his real passion is geometry, but I also know he very skillfully applies physical concepts in machine learning problems. And in general, he works in the broad area of foundations of machine learning. He has many merits and many achievements. Just let me mention a very impressive list of fellowships. So he's a fellow of IIS, fellow of ACM, fellow of IEEE, and fellow of SIAM. I think you collected all fellows one can get, at least all the main ones. So without waiting any longer, Professor Bajat, please go ahead with your talk.
Thank you. I will go into full screen mode. I wanted to start off, of course, by thanking Shalab and Gugan for organizing such a nice workshop. I wish I had been there. I had almost made it there, but maybe another time. Please interrupt me by speaking out if there are any questions. And of course, if there are things online, I think the chairperson will indicate to me as well. So the topic of this lecture is partly covered by the title, but what is hidden is a new method of both reinforcement learning and also global optimization. So I'd like to explain that now. So if I want to go into full screen mode, I can view, how do I go there into full screen mode? Is this visible to everyone? Is it large enough? Okay, good. Oh my God, I did something wrong. I think it's play that goes into full. Okay, very good. So this is joint work with a master's student, Garvit Bansal. He's in physics from IISc Pune, who's been visiting me for his master's thesis this last year, and Min Nguyen, who's currently at Microsoft. He did his PhD, he was in mathematics. And of course, the ... means there are several other people in the lab who some of these ideas were bounced off of and are definitely collaborators. So I'll start off by telling you what is some of the inspiration behind the methods that I will explain. And that is taking lessons from nature. So nature has taught us many things about emergent biophysical properties of how inert matter comes together and forms, things from molecules, starting from atoms and your DNA and your RNA to organelles and cells and tissues and organs to humans and animals and plants and so many things in a marvelous, somewhat symbiotic relationship. But the mere fact that these things can come together and learn to discover how to coexist as well as have even emerging properties, which are far beyond just the sum of the whole. And so this inspiration is, can computers be programmed? Because computer programs are inert matter. And if I give them the right energy, can they come together by interaction and start to discover new properties, which are akin to answering the question, can computers not only learn, but can they start making, multiple decision making as we go along? So I'll try to show you that some of this is actually not only already happening, in its genome in a capsid and also an envelope. And there are these spike proteins that it uses to gain entry into the cell. So it uses it like a Trojan horse. It signals the molecule sticking out of a cell, and the cell that it infects are the immune cells. And once it infects it, it snips its genome and retrofits it into the genome of the immune cells. And so once infection occurs, immune cells in our body, which are very strong, um, build antibodies to take off some of the infection, which are often called antigens. But a infected virus, instead of producing antibodies to clear infection, produces multiple copies of the same virus, which then buds out and takes this part of the lipid membrane that forms this envelope. So a cleverly designed emergent property of how DNA, nucleic acids, and proteins, and lipid membranes, and other proteins are all part of this machinery. And interference requires ways of understanding this life cycle that several biologists and biophysicists have been studying for a long time, such that you can interfere with them. And I'll tell you how one thinks of computationally designing such things. And maybe now with machine learning, we can discover better drugs than what has occurred before. The process of interaction, of course, happens amazingly at multiple scales. There are close encounters and far encounters. There's the electrostatic potential, which is like this video should play, is like a gravitational pull, but here it's the electrostatic pull. Negative is red and positive is blue, and the positive potential of the target attracts the negative potential of the interfering molecule. And if there is a balancing or a canceling out of the negative and positive, what you're getting is something which is minimizing its free energy by coming together. And I'll explain this a little bit more as we go along. So this is the kind of inspiration and why this became so much more popular, because the SARS-CoV virus uses a similar mechanism. It doesn't infect the immune cells, but it infects different cells through the ACE2 receptors rather than the CCR4 and CD4. But that's, for our study today, is kind of immaterial. So I'll jump into what the specific targets are and try to encapsulate it into a problem of optimization, which we then convert into a problem of learning and, of course, reinforcement learning. So here's another lesson of how we were computationally designing such tools. If you look at, some of my mouse has disappeared, but if you look at the picture on the left bottom, then this picture shows you a red-colored molecule and a blue-colored molecule which seems to be folded, and it matches the density of the cryo-EM map. So what is this problem? This is like a little puzzle that we have solved. When I say we, the collective we has worked on this problem. And we are revisiting this problem now in the guise of how we could mimic this with machine learning. So what is the issue? The issue is that when you discovered the structure of the red protein in the lower left, the initial, it is in an environment which is like in a crystal form, and you use X-ray diffraction to find this molecule structure. But in its nativity, this molecule actually folds by itself into a different form. And one wants to discover the structure in its nativity. And so one uses very coarse-grained methods like cryo-EM, which are not at the angstrom level, but at the nanometer level. But you can take the X-ray structure, and if you can match it with the density of what you've discovered by this other modality, then this gives you a feasible configuration of the molecule in its nativity, not in air, for example. So the methods that people have developed, including students who had worked with me, was using very rapid fast Fourier correlations, using non-uniform fast Fourier transforms, so that you can quickly align the red molecule flexibly with the green density of the cryo-EM map. What we revisit now is saying it's not the final target that you want to optimize, but think of it as a dynamical system that dynamically folds into its new environment. And the way you think of this is you want to mimic nature. If this molecule was in air, it was in a different environment. And if the molecule is put into its native cell, it will assume a different configuration automatically. So can we train our computers to sense the environment and learn this dynamics, this unknown dynamics, by the change in the environment? Because once it learns that Hamiltonian that governs the changed environment, it will always find its new, what we call free energy configuration. So if we mimic such a thing, then it turns out that what we are asking for is learn the pathway to your minimizer of your free energy, not just the final configuration. And we can, by reinforcement learning, learn such dynamic pathways or decision-making stochastic processes. Now, what are these Hamiltonians? A lot of research in the last, 50 years or more, the grand challenge problem was to build better and better models by using human intuition and empirical fitting. And these are right from the coarse-grained molecular mechanical models of the molecule and also models of the environment, which are the solvent molecules, solvent models. So these are simple models of both the molecule and the solvent. And the reason is molecules are like soft matter. They live in their native, environment, and you cannot treat or consider dynamics of the object as if it was in air and then suddenly guess its dynamics in a changed environment. You want to learn it in its nativity because that's where the interactions occur. Of course, these molecular mechanical models were replaced very quickly by statistical mechanical models. And so hence, these are statistical biophysics models. And right down to things like density functional theory and all atomistic. And clearly, there are mechanisms where this is relevant. So this is an example where simple mechanical models of these first two types in combination can emulate some aspects of hemoglobin, which is this animation on the right. This also can possibly simulate this, docking behavior of shape complementarity and electrostatics complementarity. But when it comes to things like ion channels and selectivity of ions which are filtering in our neurons, which are causing for pulse trains in the neurons, this is at this scale, the physics is completely different. And this physics is that of a stochastic, process, and not just a simple Brownian motion, because the lipids behavior and the ionic behavior has to be modeled. The environment is very noisy. So these traditional models break down, and hence one starts to look at, more complicated models of density functional theory with polarizable solvents and so on. But to complete the story, let's first start to walk, and then we can start to hop, skip, and jump. So the simplest model, like I said, is that of a molecular mechanical model of treating the molecule as a lumped parameter system, which has atoms connected by bonds, and the torsion angles are all modeled. They are all distance-dependent potentials, which are van der Waal and electrostatics, and polarization and electrostatics. Now, these things are both what we call Hamiltonian energy forms, models that people have studied and built. In our process in learning, what we'll be doing is training with these models, but then discovering our own Hamiltonians. And I'll show you the process in which we follow how we discover our own Hamiltonian. So the name of the game is learn your Hamiltonian, because the Hamiltonian captures how you will move in that specific environment. And if you change your environment, then you can learn the new Hamiltonian, update your existing Hamiltonian. But this is just to give you an example of the complexity and also the multi-term nature of the pre-existing models that existed. There's always in the Hamiltonian, this is one form called the Helmholtz free energy form. There's also a balancing with the temperature and the entropy. So energy is constantly, counterbalanced with some level of disturbance or some level of what we can call the entropic vibrations. Uh, and of course, as you increase the temperature, these vibrations will cause like more noise in your system than the true energy of what is part of the drift term of attracting potentials. But this schematic here is also saying don't think of objects when you're learning from nature in isolation. You always have to think of it with respect to the environment. Why do they say water, which is this little Mickey Mouse, is the miracle of life? Is because without water, this structure has no consequence. Uh, it acts as a screen. It also acts like giving it glue, as hydrogen bonding, and so on. So if I want to consider what is the metastable equilibrium state of a structure such as a biomolecule, then I have to learn to optimize this free energy potential. Uh, and you're searching for the configuration which satisfies this free energy. So if I'm going to use this principle, we'll try to see how we can make it computational efficient in our reinforcement learning. The challenge, of course, is tremendous because such molecules are very high dimensional. This is just a simple, hierarchy of saying what are the possible motions. This spike protein that you see up here is the entry mechanism of the HIV. It's a very flexible and it's very cleverly designed in its conformational to conserve its binding regions. What that means is it doesn't expose its regions to dock and fool the defenses till it comes close to it. So it changes its conformations magically. Now, when we say magically, it's not smart, it's not alive, but yet it has captured this intelligence in its multiple, chemical forms that it's designed. Each atom or each group of atoms is like a sensing molecule that senses how it can improve itself better. That's how these molecules also mutate. So I'll come back to this to show you why this high dimensional factored spaces can be used for our benefit. Uh, but the fact that in this example itself, this factoring is of SO3, which is a complicated space over which to sample and learn, is something that by now mathematics has given us very nice tools and we have to harness them also, otherwise we'll be lost. So with that, I'm going backwards. With that kind of a prelude, let's start thinking about how we learn how to do this basics of problems called molecular docking, or saying, if I give you two molecules, can you find the configuration? And this is even if it is rigid, what is the translation and rotation, which would be what we call in the SE3 group, translation and rotation, which is six-dimensional, of how molecule A its best configuration with molecule B in what we call the binding configuration. So, and the bottom part is what we call a docking score. And this again is kind of mimicking nature, saying, The docking configuration is the one that maximizes the reduction of free energy. So if you took molecule A and you thought of its free energy to be EA, and molecule B and its free energy to be EB, then if you looked at the delta E, which is the difference if the two molecules were together, and this difference, if this is very strongly negative, then these two molecules can reduce their free energy by coming together. That is a model of, or a scoring function of how to say, what kind of affinity you have with each other. Well, if I can come together rather than stay in isolation and minimize my free energy even more than my individual free energies, then that is clearly going to attract each other so that they can come to a lower potential well in the energy landscape. So we mimic this, of course, mathematically. Rather than first go to big terms, the simplest way is to take a complex function on the molecule A. You think of the red atoms on the left figure as the inner core, and you give it a complex value, and you take a real function, which is the green function. And now, if you were to overlap these two functions by a cross correlation or a convolution in motion space over translation and rotations, then if the green green overlaps, that will give you a positive real number. And if the red and green overlap, that will give you a complex number. And if complex interact, that's like two cores clashing, that will give you a negative real number. So this is a nice penalty function that enhances the green-green overlap. And you're searching over all possible configurations for the green-green overlap to be maximized. So this gives you a mathematical way of going back and solving the problem. So today, if I call classical machine learning, has come a long way in coming and solving such optimization problems. So hence we cast our optimization problem as a machine learning problem. And the simplest way that we've done is by deep learning, which is using differentiable dynamic programming. So we say, if you're wanting to find a minimizer or a maximizer of a function f of x, then let's go back and come up with either an approximation of f of x with different loss functions. But as we look at it, we are going to compute its gradients and follow the gradients to this minimum path. And there have been many schemes of computing such gradients. You can also compute these gradients by using adjoint methods. So as you're thinking of your flow, using one of these fixed rules, your gradient is being regularized. Eta grad, RMS prop, Adam, and Nesterov Adam are different ways of regularizing your update, because the final thing is, what is your choice of gradient and what is your update, so that you will converge to a minimum. But there's no guarantee that you will converge to a global minimum. And also, this landscape, is not as complicated as some of the landscapes that we encounter in stochastic free energy formulations. Moreover, the simple rule is not data dependent. It's like a skier going down a mountain. He's saying, if I give you several attempts, you wouldn't want to follow the method of only a stochastic gradient descent. That was for efficiency. You want to come up with customized gradients. Hence, a lot of work was done on building natural gradients, or even, different kinds of what we call policy gradients, which are TRPO and PPO, proximal policy optimization methods. But they all have one limit, and that limit is that while you can come up with good gradients, your gradients are not often stabilized. So most of your training is always going to be stochastically, hovering around your path. And so it's like learning in a non-smooth way. You're always constantly using the stochastic gradient. So that stochastic gradient is based on how good is your approximation of your loss function at each stage, and that being noisy, the gradient of that noisy loss function is even worse. So we pointed out a lot of these, saying that when you're doing even physics inspired by looking at Schrodinger's wave equations or PDEs, if you don't take care of some of these additional features, you're not going to be able to guarantee any kind of generalizability. So this became the motivation of the method that I'd like to talk about. But before I do that, I have to, of course, mention the Nobel Prize in Physics, which is awarded to computational biophysicists who are like computer scientists. So there's hope for us computer scientists to win a Nobel Prize one day. Uh, the first is, of course, Hopfield. So his idea was, don't think of the parameters of your neural network to be just values. Think of them, giving them a physics. Think of them as endowing them with an energy Hamiltonian. So the model he used was the Ising model of ferromagnetism and paramagnetism, saying that if each of your parameters was like a spin, it can take on the values of spin up or spin down, satisfying this energy Hamiltonian of pairwise interactions and individual, which is given on the E on the left. And this Hopfield network is like saying my parameters are behaving as they were magnetic spins, and so they'll come to an equilibrium, except the energy landscape of this somewhat large parameter system is very frustrated, as you can see in this landscape picture. So if I take some random initialization, to find the global minimum is never guaranteed, and all deep learning can do, and even many of the policy optimization methods will find a non-local minimum, but it will not guarantee that there is not an existing potential well even further down. So hence, generalizability suffers in such models. But nevertheless, it gave us great inspiration. Along came, of course, Hinton, who discovered together with Sejnowski and Ackley, and then he worked also with other people in producing a probabilistic version of the Ising model. He's saying, think of your parameters as being part of a sample probabilistic distribution. And so the probability of the spin taking on a value 1 is given by a Boltzmann-like distribution. There's a partition function z, and then I'll tell you how this comes into play in building the best likelihood of these parameters settling into this minima, where, of course, you're maximizing the probability, distribution of this being the most likely distribution of this being the configuration that the spins will settle into. So clearly, these were landmark methods that have now become much more sophisticated over this last decade or two. So taking inspiration from that, the method that I like to explain to you is something we call learning optimal control free energy flows with differential policy optimization. And each of these terms is important. We're going to use different forms of free energy. We're going to use optimal control, and we're going to use differential policy optimization. And what that means is it's not like traditional reinforcement learning, like soft actor critic or PPO or any of the other methods. Both those are, or Q function learning or double Q, they are forward backward methods. Means you have to go through a path, evaluate your reward and a value function backwards, and then you go back and optimize your path. In this differential policy learning, we directly go forward in our search. It's like having a value function which is learning along with you and correcting every step that you make as you go along. And this is done by this nice form of in physics called Hamiltonian dynamics using something we call the optimaltonian. But the other part is that the loss functions are also adaptable, or the reward functions are adaptable, as I'll show you. It is not a arbitrarily chosen reward function. So you learn the reward function as you go along because you learn it from the environment and how difficult it is to move in the environment through interactions. So that's another feature that is different. So the other property that I would like to explain is that this method, by its very nature, is going to be also a sample-efficient reinforcement learning method. So how do we do this? So we treat the, black box, and later on I'll make this into a white box optimization problem by not only finding X star, but finding the entire path and learning this path and its correction at every step, at every episode. So DPO progressively learns a global optimizer policy through reinforcement learned Hamiltonian dynamics, trying to find the global optimal solution by correcting the path it takes to find it. This animation that you might have seen is kind of illustrative, but let me first explain. What you're seeing here is like I'm successively learning the approximation of the mountain without having to learn the entire mountain for every run that I make down the mountain. So every descent by Hamiltonian flow gives me better knowledge of my current approximation and how much the error was in my current approximation so I can optimize my path. So I'm searching over all possible paths and also selective approximation of the energy landscape only on the paths that I tread. So the way to do that is to first cast the optimization of learning such dynamical paths as a constrained optimization problem. And there are a few details I'm skipping here, but essentially you can reduce this dynamics learning as an optimization, as an optimal control problem by satisfying this, what we call the action Lagrangian. This action Lagrangian is the kinetic energy of your learning path and, of course, the potential energy. So if you minimize this subject to the constraints of your dynamics, then this solution is a solution to this problem.
Professor Bajaj,
But yes.
if I can interrupt, I'm just curious.
Yes.
Why do you have a discount factor? So, if I understand correctly,
yes,
in
yes,
your
this is
yes, so typically discount factor is applied in financial type of applications, but does it have any meaning in the physics type application, or it's for numerical stability? So I'm just curious.
Very good question. And there are two reasons. With this discount factor, it's like a viscous drag coefficient. I'm going to give you friction in doing along the path. I can control this gamma as a function of t to limit how much exploration you can make, deviate from the mean path. So it's a natural exploration, exploitation at every step. The second thing is when I'm getting close to the minimum of my optimization problem, I want to increase the drag so the momentum I had gained, I don't want to jump over that minimum. So I control this E gamma t throughout the entire path. One, to limit the exploration and exploitation, and the second is to use momentum, but also terminate at a decent enough potential well. So this is, yeah.
Later we add first derivative term to add viscosity to the oscillator. So here it's different type of viscosity, right?
That's right. And furthermore, this is like a learned adaptable. So you learn your gamma, which is how much friction you need for this environment. You learn your momentum as you explore the landscape, finding and prospecting for global minima, all based on the potential that you want to reduce, which is you want to find the minima of this f of q.
Okay, thank you.
Or the maxima of this. And so the first step is we define this controllable Hamiltonian. So our flows are all with optimal control, but they are also governed by this Hamiltonian. So the Lagrangian itself is a action Lagrangian. That means it's captured motion within its reward function. It's because you've got a velocity u squared, which is your kinetic term, while you're searching for the minimum of a potential well. And this controllable is added with respect to, we are using currently in this form, and I'll show you different forms, where I use u to be, the controller as well. So it's like when I'm going to move, I'm going to use my velocity as a controller to my speed at which I'm trying to find my minima. We use a principle called the Pontryagin maximum principle that projects this Hamiltonian along a path. And this is the optimal path governed by the necessary conditions of PMP. I can relate this PMP by the HJB condition. The HJB condition will lead to a PDE. The PMP leads to an ODE. And this projected Hamiltonian dynamics is part of the solution of saying, for this Hamiltonian, this is the speed at which your flow will occur, including your drag coefficient, including the derivative of your potentials. Also, this conjugate momentum, which is the P form. So I've gone from only a single state Q to a generalized state, which is called QP, as well as having a control U. And this projection eliminates this U to give you a generalized Hamiltonian symplectic dynamics. Let me explain this further. I've tried to make this simpler as we go along. So what is the controlled Hamiltonian? It's nothing more than a form which is based on your state space X, its dual, which is its tangent space, as well as a control space V. And this P, which is in the dual space, is called the conjugate momentum. And this applies to both statistical physics, relativistic physics, as well as, classical mechanical physics. The F is my unknown dynamics of motion, or my policy that I'm going to learn. L is my cost to move in this environment. Q is my state, and V is the control. And this Hamiltonian is directly from the action Lagrangian that we had defined by a simple Legendre transform. The Pontryagin maximum principle tells you that the optimal solution of the control is given through the adjoint variable P by satisfying these conditions. And this is, of course, the famous Pontryagin with his students, Bolshansky and Mishenko and others, in this famous paper in 1962. So there are four conditions. The first two conditions are the Hamiltonian dynamics, which is in symplectic form. And I'll explain that a little bit downstream again. But the third condition, which is saying that if this has to be optimal, this control has to be critical. And so this criticality condition in deterministic setting is given by the third equation. And of course, the terminal condition also has to be satisfied. So PMP allows one to take the third equation and cast the V in terms of the Q and P. Hence, any optimization problem with constrained dynamics, like in optimal control, can be mapped to learning just the forward dynamics through this principle. The Like I said, what I'm telling you about PMP has also been generalized to HJB, but I will not talk about this here. So here's a very busy slide, but it explains a little bit about the inner loop and outer loop. So there are two processes going on. One is for a certain approximation of my energy landscape, I'm going to learn by forward dynamics along paths, by optimal control paths. That's what you're seeing in this figure. That's the inner loop, which is using the symplectic integrator, computing loss functions. Here, this is like cross entropy for a classification problem. The outer loop is measuring how generalizable is this model given by the generalization error. And it uses this model fidelity controller by updating the approximation. But the approximation is not of the entire mountain or the entire Hamiltonian. It's only along selective paths. The paths I've visited, I'm making it better, and then I'm trying from a different initial condition and making it better. I'll skip over this. I just wanted to briefly mention we applied this to and compared this to many of the classical methods, and it shows very promising results. And so we are very excited about this method. We also proved certain nice bounds. So the first thing is, one is doing this both deterministically and, as I'll show you next, stochastically. It's learning using these trajectories, which are optimal trajectories. It's learning the optimal policy, which is your transition density governed by your, the dynamics of decision making that you're going to make. So this is all through interactions with the environment B. So each time you are querying the environment at certain points, checkpoints along your trajectory, to see how far away am I from, a better trajectory. And of course, this is done differentially. So this little function G assesses the performance of the current policy along the path. And the update or the relationship in this first order case, we have a second order case also, is that the capital G, which is our policy that we are learning in our system, is given by this symplectic A times the differential of this scoring function G. To make this a little bit more practical, I just wanted to highlight what this algorithm is. Again, I'm not going to go through line by line, but the main parts. So what are we doing? We are learning a policy directly in our neural network or in our architecture. And this policy is the transition function. And this dynamical decision-making policy keeps updating by using this scoring function, which we initialize by a random scoring function. But the scoring function learns simultaneously to your policy learning by looking at various sample points in the environment, the interactions, and measuring the scores. The scores are given in line 4. Furthermore, it has this very important principle. If I learn one path, I want to learn a better path, but I don't want to deviate for parts of the path where I was very good. So the inter-episodic memory, and we also have a intra-episodic memory, allows you to keep checking that any new policy doesn't deviate from the previous policies on samples on which previous policy already performed well. So this is like, I never unlearned something I've learned. And this gives an active thing that you can keep continually learning. So using, Rademacher complexity and also Lipschitz constant smoothness of both the policy approximator G theta and having a trained policy which is also smooth, one can prove a generalization gap bound. Again, I'm skipping details, but it's in our paper. We can also show you the tightest sample complexity bounds, because we are not sampling the entire environment. We are only sampling it along the paths we are visiting and quickly converging to the optimal path or the optimal policy. And there's also a convergence rate, which is, based on the number of samples as well as, how smooth this, based on theorem one. And we also show a regret bound. But let me get into something more interesting. And that interesting thing comes with respect to stochasticity and statistical physics. So when we applied this originally, it's basically saying it's your choice of your free energy. And your free energy, if you make it more sophisticated, clearly it makes the problem more complex. But clearly that is where we have to do, because if I just go back and do it, I will discover, molecules of a certain configuration which has low free energy, but they might not be the ultimate, deep potential well of a very stable configuration. So the search is a repeated search of prospecting for better configurations than the ones based on your current model E. So to do this, we go back, and if you recall this free energy term, we incorporate at least entropy, and I'll show you how we incorporate even something called the chemical potential in our Hamiltonian learning. So we change the problem into saying our objective function, which was my loss function LSX, which is in the top right corner, is now captured in an expectation form balanced by a KL divergence of this entropy. And this form comes naturally from the entropic term, as I'll show you with respect to an elbow. The optimal control problem converted into a stochastic optimization problem subject to a stochastic process. So what you can see in this optimal control formulation is you've got, the state is now changing as a stochastic process. And your choice of what type of stochastic process is up to you. If you're taking a Wiener process, or you're taking a jump process, and so on, that's what you're saying, what you want to subject and constrain your hypothesis space of state changes for your policy of changing your state. And for this, we can show you the optimal stochastic control flow. So what we also am showing you in this figure is, to do this, we have to learn three probabilistic densities. One is the unknown F, but we also use another density called G that's colored in green. And we also have to sample from multiple initial conditions, because for this, given the stochasticity, once you look at the distribution of starting points, this distribution of starting points is governed. It's like trying to find your way down and learning not only from one starting point, but from multiple starting points, because then you can explore better ways of going down the mountain. And maybe you discover that, it's like climbing Mount Everest in the maximization case. The north face is completely impassable, but the south face is easier, and that's why most people tend to go from the south face, so they can start from different initial conditions. So the learning becomes a simultaneous interaction and sensing and knowledge acquisition process. It's like a physics agent, like a physics student who might start off in grade 1 or graduate grade 1, and then starts becoming graduate grade 2. And so it keeps learning how to do. It learns more physics, and it learns how to solve its problem better, because it wants to avoid local estimations, which is, and also make oversimplifications. This is the spherical cow example in physics, and of course this is a well-known cartoon of, if you're only locally sampling and locally making estimations, then you're always guessing the wrong answer of the total object. So this stochastic DPO continually learns the stochastic action process for global minimizers via a controlled Hamiltonian, and this is achieved by machine trainable biophysics agents that update their free energy through progressive interactions with your generic training environment. So each time you're learning how much is the value function for not only your loss function, but also the entropy. Was the entropy estimation that you made, how far off it was, and how much is what is called your sample complexity or the length of the path that you took, which is often captured by the chemical potential in physics. There's also a volume measure, but for now we are just considering this. So just like the static PMP, there is a stochastic Pontryagin, and this leads to a stochastic differential policy, and I'm going through the same methodology, but now with stochastic processes. So I cast my stochastic optimization, which is in orange on top, constrained by a stochastic process, into a stochastic optimal Tonian, which is in the middle, which is then using stochastic PMP reduced to the optimal action policy. And the dynamics is now a stochastic dynamics of both the momentum and of the optimal control. And the Hamiltonian dynamics is a stochastic process also given by the symplectic structure in matrix form, 0, 1, or 0 minus I 0 with the gradient of the Hamiltonian, which is the reduced Hamiltonian, times this epsilon kappa. And this is kind of important. So let's take some examples, and I hope this will make it a lot clearer. So in general sense, you're saying the solution of how you will learn is your state can change stochastically, governed by your learning the epsilon of your path that you want to choose. And your control or your conjugate momentum also is a stochastic. So both can be stochastic. This is the case for when I'm trying to find how to build selective ion channels that only allow sodium to go through and not potassium. So if I want to discover these very selective channels, we've got sodium channels, potassium channels, and calcium channels. They don't allow anything else than the specific chemical type to go through. There's this other case, which we've often looked at for the carpole problem that you've seen. So, oh my God, why is that movie not playing? But you're all familiar with the carpole problem. But what happens when you want to train it with dissipative forces like wind or there's an earthquake? So when there's an earthquake, how can you build? This is like an idealized version of making earthquake-proof walls. What is your control strategy? It can't be a fixed strategy independent of the magnitude of the earthquake and the magnitude of the dissipative winds. So what you want is you want to change your state here, possibly deterministically, but the control is going to be governed by the stochasticity of the environment, so the control is stochastic. In this other case, where think of a drunken sailor, the state of this drunken sailor or the drunkard's walk is stochastic. The control could be your friend who's not drunk, who's deterministic. So by adjusting these epsilons and k's, you get all the range possibilities of stochastic state changes, stochastic control, or deterministic state changes, and deterministic control, and so on. And these are all captured through this Hamiltonian, the stochastic Hamiltonian. And the reinforcement learning way will give you the correct dynamics of how you wish to flow. And look at this. This dynamics is like giving you stabilized stochastic gradients. They are the right way to flow through in your solution, not just ordinary gradients. So this transformation helps you with that by capturing the environment where you want to be learning your task. So don't learn your task independent of the environment. So I'll conclude with a few final things that we are applying this to. This is, we are applying these physics agents to discover new materials. New materials here, these are what are called halide perovskites. And these halide perovskites are very much used in lasers, they're used in solar cells, in LEDs, of course, in photocatalysis, catalysts. So our goal here is to use this to come up with new perovskites. So the plan is not only to learn, existing ones, but how do I go back and starting from some existing configurations, climb the discovery mountain and finding a better potential well in which I can fall into, which is something which is improved. And the way we do it is we have to resort to density functional theory. And so this is
Professor
a
Bhajar,
well-known thing in physics.
excuse me, I think we
Yes.
have to conclude in the interest of time and maybe give time for a couple of questions. Sorry to
Okay,
interrupt
so
you.
this is very good. I lost track of time. Let me conclude by giving my conclusions. There was a little bit more, and I should have paced myself better. But with this, the next step of challenges are we have been doing stochastic DPO with sequential Monte Carlo for discovery of new materials. We are also doing predictive topology optimization in stochastic dynamic networks. There's, of course, increased challenges with respect to sample complexity, generalization for stochastic DPO, and there's also this notion of gamma convergence, which I didn't come to. But thank you, and I lost track of time.
No problem at all. Are there any questions? I think we still have time for one or two questions, if there are. Yes, please.
Yeah, very nice talk, Chandrajit. So, one question is regarding the SD formulation that you had. Do you assume knowledge of the drift and diffusion terms, and or are they unknown?
They are unknown. So this is like saying, like unknown model free, you're saying learn the unknown stochastic dynamics, the drift term and the diffusion term, as you're constrained by optimizing a cost functional, the optimal control formulation of learning the dynamics. So that's what you're learning. You're learning the stochastic dynamics, stochastic decision making.
Sure. Okay, thanks.
Right. So the combination of the Q and P are both either both are stochastic or one is stochastic and the other is deterministic. And you have to, in stochastic environments, learn stochastic decision making.
Are there more questions? If not, let us thank Professor Bajaj for this very interesting presentation.
There's one other slide I had, which is saying if they are interested PhD and postdocs, we are recruiting, and also faculty visitors are very welcome. We have a nice program to have people come over and do research with us. So please don't hesitate to contact me. Come visit us in Texas, and we'll show you some Texas hospitality.
Thank you.
Basically, there's funding available for visitors.
Gugan, maybe you want to make some announcement.
Sure. Okay. Thank you, Professor Bajaj. This was a very nice talk. So we will now have a tea and coffee break, and we will assemble at 10. What time is it? Yeah. So we will assemble at 10:30. Okay. Thank you.
Okay. Bye-bye, everyone.
So maybe one more quick announcement. So we would like to collect your feedback about the workshop so that we know where we did well, where we went wrong. So if you go to the RL workshop webpage, there is a tab titled feedback. So if you click on that tab, you should see a form open up. In that, your name, email is optional. So you can, openly criticize or appreciate whatever you liked or disliked about the workshop, but we request that you go and provide your feedback. Thank you.
from IIT Madras in 2010. Then he obtained his PhD from UT Austin in 2016. And he was for a few years, actually quite a few years, about 5 years, as a research staff member at IBM New York unit. And now Kartikeyan is a research scientist at Google DeepMind India, here in Bangalore. And he's in that Google DeepMind research unit. He is a part of Machine Learning Foundation and Optimization team. The research interests of Kartikeyan are machine learning, coding and information theory, and recently causal inference, bandits, and reinforcement learning. And today, I guess we'll hear a talk about online bidding. So once you are ready, please go ahead.
Screen is enter full screen. Last one. Yeah, can you all hear me? Thanks a lot for the wonderful introduction. So I'm glad to be here to be giving this talk, and I thank the organizers for actually inviting me. So contrary to the previous talk, this will be a bit less useful and more theoretical. I hope that is fine with the audience. So let me actually get started. Okay, so this is actually it's a toyish version of a useful problem. So let me just change my description of this problem. So this is called online auto bidding with ROS constraints without knowing the value. I know it's a mouthful. All it says is that we are going to consider a bandit problem in ad auction systems. Okay, I'm going to describe what these things mean and set up the problem, tell you what the close related work is, what the challenges are, and finally I'm going to tell you a very simple algorithm. Okay, so this is joint work with This is joint work with Sushant Vijayan, who's a PhD student at TIFR, and postdoc Swati Padmanabhan at MIT, and all my Google colleagues, Arun Sugala, Diwang, and Jia Feng. So I don't yet have an archive preprint, but we are soon going to put it because the work just got accepted to the WebConf 2025. So we are in the process of just finalizing the camera-ready version. Okay, so you're just going to see something that's going to be just out. Okay, so my clicker isn't working, but that's fine. Okay, so I'm going to first describe what the auto bidding problem is. Then we are going to basically look at very key recent works. As you can imagine, this is an ad auction system, so it's a lot of money, so a lot of people are interested in this problem. So people have done various things before us, and there was one challenge that was left, and in a particular setting, in a stochastic setting, we were able to actually resolve that challenge in this paper. So I'll just talk about our algorithm approach and the regret results later. So I'll spend quite a bit of time here. I know it's a literature review, but I just wanted to also give you a sense of what is the complexity behind the problem and why we are solving it in a different way. Okay. Okay. So what is the auto bidding problem? So if you're an advertiser, let's say you're Walmart or you're Disney or you're Hotstar, whatever, right? You want to advertise your latest movie, your latest product. So that's called a campaign. Okay. And the campaigns don't last very long. They are very short campaigns, which means if you're releasing a movie this month, you're just going to run a campaign for maybe the next 1.5 months or 2 months. Okay. So what does running a campaign mean? You have an ad, in fact, somewhat customizable ad, and then you want to find opportunities where you want to place the ad to people, right? And so what else? So what you can do is that you have some money, advertising money that your marketing team gives you, and you can actually place bids in online platforms. Okay. So what does an online platform actually do? Let's say it's a web page like Google search, or it could be Bing search, it could be anything else where users come and then interact, and you want to show ads. So you have some placement opportunities, right? And you are selling that particular place to these advertisers. Okay, that's what you're trying to do. Now let's say there are multiple advertisers who would be interested in this particular slot, because a particular type of user would come, and these advertisers would say, if these type of users come, I would like to show my ad, and I'm willing to pay this much money for this particular placement. And that's what an advertiser needs to tell the platform. So there's a bidding that is being made. Okay, and so all the bids are collected. So all the time, all the advertisers won't be on all opportunities. There is a subset selection that happens, but that's not very important for our problem. You can think for this particular talk that there are just the same pool of advertisers, and every opportunity comes, everybody places bids, just for the sake of simplicity. Okay, so you place a bid, and suppose you win the bid. So the platform has an auction system. So I'll just detail one example of an auction system. So the auction system does two things. It looks at the entire bid distribution, the empirical bid distribution, and then it decides the winner, and it also tells the winner what price they have to pay. Okay, so there are two things the platform actually tells. They look at the bid distribution, they pick the winner, and they tell you what price the winner has to pay. Okay, and suppose a specific advertiser wins the bid, it will be communicated to the advertiser, and you will be allowed to place your ad. I mean, it will happen automatically. The winner's ad will be placed here. Okay, then what happens is that depends. I mean, maybe the ad is not interesting, the user doesn't do anything, so it's a lost opportunity, but you paid for it. Okay, so you bid and you placed your ad, but nothing came out of it. Or what could happen is maybe the user clicks, then goes on to your website, maybe they rent a movie, they download a movie, right? All of that are basically values. It's not important what actually constitutes value. You can think for this particular talk that just click through is basically some value. Somebody is paying for just traffic arriving at their website. Okay, it's just a simple system. Now the winner gets the opportunity, and then the winner gets to see the value. It's very important that had I given this opportunity to some other advertiser, that advertiser would have seen its value counterfactually, but you would not know that. You would know the value only if you win the bid. Okay, so that's very, very important. Okay, and it could be any one of these things, either a click or a buy action or a page visit and so on. We'll always assume that there is some simple bounded distribution for what is called a value. For your mental picture, you can just think of this as click-through rate. Okay, right. Okay. So, but what exactly is the problem? The multiple people actually bid. So you have to make sure that your marketing team's budget is sort of met, right? So you shouldn't overbid for an opportunity if you knew that traffic is not actually getting you anything that you want. You don't know a priori that is the case. Maybe you have an opportunity in a specific website, but you go and advertise, maybe only you get 5% of the users in your thing. But let's say you went and advertised in a very different website, then maybe you get 15% traffic. You would rather bid more for a place where you get more value, right? That's what you would like to do. But you have constraints, right? So we'll see what the constraints are. Now I just want to describe a little bit about the auction system. Just want to say to all the game theory folks here, I am not trying to consider any auction design here. So the objective of this problem is not to change the auction or anything of the sort. The auction is fixed. So there's no mechanism design problem or anything of the sort. It's from the advertiser point of view. Okay. So for example, for this talk, for the mental picture, you can assume second price auction. What that means is the following. you look at all the bids, you pick the max bid, declare that person as a winner, but then you charge the person the second best bid. I mean, if you didn't know the second price auction, it might be surprising to you why I would not charge the max bid. Why would I be charging the second best bid? Turns out that this was a Nobel winning idea behind Vickery mechanism, and apparently it has some very interesting truthfulness properties, which means it will force you to reveal your true utility of this opportunity. If you knew it, and let's say and you're bidding, if you knew the value of this opportunity and you're bidding, it will force you to reveal your true preferences. You can't hide and you can't play games, right? But we are not interested in the auction design part. We are only interested in the fact that there is an auction. You can think of this as second price auction, and you're just going into the system. We are talking about the bidding problem, like how do you actually bid with budget constraints. Okay. So looks like I need to. So I need to be here all the time. Okay, so as I said, the auction system is fixed, but in life there is always finite money, although we would like to have more. So even a big advertiser always also has finite amount of money. So over T time slots, you are allowed to spend row dollars per time slot, or row rupees per time slot, whatever the unit is, right? That's what you're allowed to basically spend. And one more important thing, the most important thing is you must get profit, right? Otherwise there's no proposition. So you have to make sure at least that the total value that the bidder gets is at least the price the bidder pays in total over T time slots, right? In fact, there is usually a ratio. You can normalize it and you can just consider this to be just an inequality. It doesn't change the generality of the problem. Usually what you want is the advertiser would say, I want 20% profit. I spent this much, I want 120 times what I spent as my revenue, okay? So you can factor that, but you can, for simplicity, you can just consider this that I just want non-zero profit, that's it, okay? Now, all everybody wants to do, or the platform wants to do, in fact, if the platform is not good, and if it's not conducting the auction correctly, then nobody would be interested in bidding for your particular opportunity, right? So everybody is interested in maximizing the total value, right? Otherwise the bidders won't come, they won't be incentivized, right? But from a bidder point of view, these are the constraints. You want to maximize your utility, but with a profit constraint, and there is a budget constraint because there's finite money, okay? Okay, so now let's get into, so is the setting clear? Just wanted to understand at a broader level, is the setting clear? Is there any questions that you guys have? Okay, so I'm assuming it's clear. Okay, so now let's get into some notation. Unfortunately, these four things will keep occurring in the talk, but I'll try to keep the notation to a minimum. So BT, self-explanatory, is the bid that the advertiser places at time T from a set of finite bids. I mean, in practice, you would like to have a full distribution over a continuous support, but the thing is, we are just discretizing. Think about the fact that we are just discretizing it. Okay, so there are B bids you can make, right? Maybe in intervals of 5 cents or $1 or whatever, and that is the support of the bid distribution that you can use, and you can place a bid at time T, right? It could be from a random distribution. It could be a random action also. Now, once the bid is in, there is a pricing function and there is an allocation function. These two are environmental variables that are not under the control of the advertiser, because the platform auction system decides what the allocation function is and what the price is. There are two very simple properties. There is one simple property governing this pricing function PT and XT. If you bid more, you would like the price to be also more, because the platform will think, okay, this person is willing to bid more, so it means I have to charge the person more, or at least not less. And then the Boolean allocation function should also increase, right? If I'm bidding more, I must have a higher opportunity of actually landing the thing. Otherwise, the auction isn't fair, right? So we just assume that the allocation function and the pricing function are monotonic in the bids. That's all. That's the only thing that is being assumed. So there is no other assumption here. Okay, so it could be very nonlinear functions also, and they are very nonlinear functions even for second price auctions. Okay, So then you place the bid and let's say you won, then you get this value which is the value at time t upon winning. Let's assume that Vt is a random variable from some bounded distribution, right? Now I'm going to make one important assumption. It is a toyish assumption, I do agree with it, but a lot of prior works and so far a lot of works have considered this setting, so we are not very far away from the related work. So I'm going to assume that once you place the bid, right, the pricing function, the allocation function and the value, the triplet is IID over time. So it's drawn from some distribution, but it's IID over time, okay. So you can think of this as some sort of an average allocation rate, average pricing rate that you will get for bid B, and the average value that you will get if you landed and you won the bid, basically, okay. Yes, so is there a question?
I just want to understand your notation.
Yes.
So here B is a vector of all bids, or this is like a bid of one user, and this PT of B can be different from B. Is that correct?
Yes, PT of B, think of it as a function, and the function is being randomly sampled.
I see.
And xt of B is a function, and for any B you give, xt of B is something the environment actually gives you.
And is B a vector, or is B is it
So
the
B is a scalar, just a
like
single
bid
number.
of one user?
Yeah, one user. I don't know what the bid could be, so I'm just writing it as a function. Okay, so the platform reveals a function, then you give me the bid BT, therefore I'll evaluate the function at only BT and give it to you, right?
Sure. Thank you.
Okay.
Basic question. So you pay a price even if you don't win, right?
No. Only if you win. Only if you win. I just said price at time t upon winning with bid. Okay, so this is related to your question. So the actual variable that matters is the price actually paid, which is the allocation multiplied by the pricing function, and the allocation is a Boolean variable. Therefore, if you won, then it will be multiplied by the pricing function. Okay. Okay. So so suppose you knew everything, like the value was actually shown to you before you bid. Usually it never happens, but suppose that is the case. Suppose somebody gives you an estimate of the value, and let's say we assume it's like perfectly accurate. It's a perfect random sample from the random variable. Then what is the problem that you want to solve? Mathematically, I said there are two constraints. So you want profit. That's the first constraint. So you look at all the price you paid, multiply by some profit function, like some factor, and the value you get must be greater than that, right? And ROS is usually greater than like 1. But what you can do is you can just push the ROS into the price or the value. I mean, you can normalize it, and you can recast the problem as a normalized version of the problem. Therefore, you can just take for all practical purposes ROS to be 1. Okay, it doesn't change anything in this problem. It just changes the support of VT, like it scales VT. That's it, right? And the last one is very simple. I have finite money always in the world. Okay, and all I want to do is I want to maximize the value that I get total. This is the actual problem. This is what the agent wants to do. Okay. In this problem, of course, in any constraint problem, I have to give you the coefficients because B is the decision variable, so everything else must be known. But the unfortunate part is that VT is not known. Okay, because it's a random thing, you have no idea, and only when you bid, you will actually get to know the value. That is a problem here. Okay. Now, I said the environment acts in an IID manner, so it gives you the pricing function, the allocation function in an IID, and the value in an IID manner. So you can basically define averages, right? So V bar is the average one, Q bar of P is the, if you add bid B, this is the average price you will pay over time, and if you're always bidding at B, this is the average allocation rate that you will actually get. Okay, so what is the comparator? Like, okay, I am playing a bandit problem, so I don't know a lot of things. I am placing a bid, and the environment reveals something. So I have to adapt myself, and I want to get my maximum value. But what is that I want to compete? Who is the person I want to compete with? I want to compete with this LP, where if you plug in all the average quantities, and if I solve for the bidding distribution, the optimal bidding distribution, turns out that because of these constraints, particularly the ROS constraint, this bidding distribution will not be peaky. It will have some spread, right? And you want to actually find out how close you are to the objective of this average LP solution. That is one objective. but you can always achieve the objective, which is become better than the comparator by spending more money, right? Because there has to be something about the constraints also. So what we actually want also is that the constraints are violated in a sublinear rate. So if I divide everything by t, okay, the violation is basically going down to 0. Okay, so basically you can have a violation, but it can be like plus root t or t to the 3 by 4, but can never be linear in t. That's what I want. Similarly for the other constraint. Okay.
Just a quick question on the second. For the second constraint, do you need QT to be lower than rho at each time step, or is it like
no?
It's
Again,
a cumulative.
Yeah, from the regret in a regret sense. Yeah.
Okay.
So rho t is fine. I have a little bit more like money, but I cannot have a linear scaling basically.
Okay.
Plus square root t or t to the 3 by 4 or anything sublinear. Small o of t is fine. Okay. So that's the problem. Okay. So any questions? Yes. So I think.
So if you think of value as number of clicks, so how do we compare these quantities? That value may be some number of clicks, but that price paid is something which is monetary. So how do we estimate the value?
That is the problem. We are going to go there.
Okay.
Yeah. So I'm going to describe the actual problem. Yes, you're right. So the value is not known. So you can't actually hope to even solve something like this, even if you have other averages, right? But actually we don't know any of them. Everything is stochastic. So we'll have to figure out how to solve the problem. So I hope from that question, I guess the problem is at least clear. So the value is unknown at the time of bidding. That's the key setting in which we are solving the problem. Okay, and revealed only upon winning. That's also another thing. It's not that the value is revealed all the time for everybody, because I mean the user has to do something, right? So the person would do only for the winning bid. So counterfactually there is no signal either. Okay. Now this is the reward regret that I said. There is an optima of the average LP times t, but you want the reward to be as close as this in the regret sense. Of course, you can even exceed this by paying more money. So you want to make sure that the constraints also have the sum of constraint ovulations over time is also sublinear. So you want sublinear rate here, sublinear rate here, right? And in this particular case, we are targeting root t, and root t, or root t log t, root t log t, and root t. Okay, so this is the problem. This is what I want. Okay, so as this involves a lot of money, a lot of people have also worked on this problem. So let me slowly walk you through like various levels of assumptions that people have had prior, some of which we have actually removed. And when you put those assumptions, first of all, how do you even solve the problem? Because it's still non-trivial even if you knew the value. Okay, so there is this. This is the closest paper. In fact, all these are the co-authors in this paper too. So they wrote a paper in 2022. It's called the online bidding algorithms for return on spend constraint advertisers. So the key thing is that you could formulate the problem in slightly different ways, but this ROS constraint is a very terrible one. Okay, because the XT, PT, nothing is linear. There's nothing. I'm not even saying anything about convexity. So it's a nonlinear function, right? There are some interesting properties about second price auctions or monotonicity of these functions. You have to use them somehow, right? So it's a very unique problem. Okay, so it's not like convex things subject to convex constraints. Okay, so what were their assumptions? Environment is IID. We have also assumed that the value is revealed before the bid. It's a very strong assumption. Okay, before you bid, I will tell you. If you bid at this B, if you got this opportunity, this would be the value you will get. So VT is almost like deterministically revealed before the bid is being placed. It's a very strong assumption. And they assume truthful auctions. By the way, second price auction is a truthful auction. I don't want to go into what a truthful auction is. Suffices to say that there are a set of auction categories which are known in the auction design community to be forcing you to incentivizing you to reveal the true utility. In this particular case, it makes sense because you know the value. This is the value you will get. Some other person would get some other value, for example, right? And the auction will force you to actually reveal your true preference, right? So you cannot like cheat or something like that. Now, but that's not very important. Now, what is their algorithm? The algorithm is very interesting. Okay, I really apologize. I should have said this. Okay, so what you do is that okay, so I'm just going to illustrate using the ROS constraints alone just for simplicity. You can also put one more constraint and add one more dual variable. A lot of things will be very similar. That's not very important. Let's assume let's just look at the ROS constraints alone, right? So you want to maximize this subject to this not being violated. So what is the natural thing you do? You just have a Lagrangian formulation. Okay, so that's exactly what this is. But in the dual space, there is an additional convex regularizer. Okay, so that is the only thing, and this is like a convex potential. In this particular case, negative log entropy. If you are familiar with mirror descent and Bregman divergences, this should be very familiar to you. So this is like this is a convex potential, right? This is just to regularize the dual space. Now, suppose basically they just solve this problem, okay, and to pick the bid I. But how do they solve the problem? The inner problem, right? Because Vt is known, so everything is known here. Everything is revealed up front, so everything is basically known. So what you do is that if you try to solve this problem in a mirror descent fashion, which means you take a small step, so which means lambda times the violation plus the Bregman divergence between the current lambda and the previous lambda, right? So you want to take a small step, but you want to penalize the metric by the Bregman divergence associated with this, and then you want to penalize whatever loss function you want, and you want to pick the best lambda, right? So this is a mirror descent step with Bregman divergence associated with the potential hedge. So what this will do is, like, if there are a lot of violations, the lambda will blow up quite a bit, right? And if there are very few violations, the lambda will just subside down, right? That's exactly what's happening here. Okay, so suppose you fix the lambda, so you pick the lambda t plus 1, so you got the primal problem, and you try to solve the whole thing, and it turns out it's not obvious from here, but if you have a truthful auction and you have these monotonicity properties, then you can show that even with nonlinearities in xt and all of that, the bid is always Vt times 1 plus 1 minus 1 over lambda. I mean, after I look at this, it looks very intuitive. All this says is that if I knew the value, there is no reason to bid slightly more than that, okay? Because a second price auction will force you to basically reveal your true preferences, which is your true value, which you knew, right? The only reason you would deviate is to grab the opportunity because the others are also bidding and so on, provided you have money, right? If you didn't have money, lambda will blow up and you will be very conservative. So you'll go close to the value, right? But if you have a lot of money, fine. I mean, I can violate it a little bit to basically grab the opportunity. Therefore, I just bid a little bit more, right? So this is an intuitive way of doing a primal dual algorithm. Yes.
This structure of PT is, I guess, influenced by the choice of the Bregman function H.
Structure of PT, you mean, or B?
Is that decided by how you choose H?
No, because once you decide lambda, this is constant, it goes away. This is the only optimization problem, and this is just whatever, I mean, it's just a linear functional in all these variables, and we use the fact that x of b is monotonic, all these things, and it's truthful, which has some properties, like the pricing function has a very particular structure. They exploit that to basically get this. This is not our result, I mean this is not even their result, it's known for a very long time. That's for truthful. Yes. Okay, great. Okay, so then you do this, you get root t constraint and reward regret. By the way, they have more adaptations of this basic algorithm. For example, in this particular case, if you knew the value, you can do something stronger. You can actually make sure the constraint violations are 0 and add just a root t log t extra term in the reward. So you can only have reward regret and the constraint can be strictly satisfied. So they show all of that for this particular, some variation of this algorithm. I'm not going into all of that, right? But the main point is this is the key assumption and they require truthful auctions. Okay, fine. Now, if you are familiar with the constraint bandit literature, you might wonder, okay, some people have solved bandits with concave rewards and convex knapsacks and so on. So how is your method related to all of those? So the first thing is the ROS constraint again plays spoil sport. There's nothing convex about it, and it has some issues, and I'll tell you what the main issue is. So what algorithms they use, so think of a constraint problem as there are a bunch of concave rewards subject to some convex constraints, so more general problem. So ours is just could be cast as it's related to this problem. So what they do is they do something very similar. There's a primal black box low regret algorithm, and there's a convex regularizer over the dual space, so they do something like primal dual. But all these primal dual algorithms rely on one important fact, which is the dual space should be compact, or if you project onto a compact space, it should not affect your regret. Your problem should have that property. So it turns out that when you have knapsack constraints, this can be proven. So you can establish that the dual variable of the average LP or the average problem, the average underlying problem, the dual space will be compact. Maybe it will be in a simplex and things like that. So you can actually prove that, right? So the dual variables are bounded. Once the dual variables are bounded, it's easy to actually sort of derive regret bounds. Okay, but the ROS constraints are not really amenable to such an analysis if the value is not known. In this particular case also, because the value is known, you can actually sort of constrain the dual variables, in the analysis. But the point is when the value is not known, essentially it's not very clear how big the dual variables can get, because V is random, like there is some randomness in V basically. Okay, so that is the key issue. When you have a primal dual algorithm, the dual updates can blow up, and therefore you can't control what the primal is actually trying to do. Okay, that's the key issue, because then you'll be too conservative and there is an issue, and you'll be very far away from what a comparator would do, right? Now there is a very recent work in 2022 by Castiglione et al. Again, they were considering a very general version of the problem like this. F is again concave, G is convex, okay, and F is a random function sampled from some distribution, G is a random function sampled from some distribution. It looks very similar to our setup, and the constraints and the reward functions, the FT and GT are revealed to you before you place the bid. Okay, so it's like the known value problem here. Okay, so they took a very interesting approach. Again, some primal dual version of what I said before, but it's a different primal dual algorithm. But the key here is that they wanted some Slater condition to be satisfied. So they wanted that the actual problem, the average version of this problem, to have a strict constraint satisfaction for some bid distribution, right? So you wanted a feasible solution that was strictly feasible, okay, and you wanted the constraint violation, the constraint slack to be at least some parameter basically. Let's say the slack is at least S, okay. So you wanted a strictly feasible solution in the interior and with some slack S, and turns out if you assume this, then you can come up with an algorithm, you can analyze the primal dual stuff, and you will get a regret of square root of T by S. Okay, so why is this? It turns out that the dual variable can be bounded by 1 over the Slater parameter, roughly. Okay, so if you just look at some LP theory, you can actually show that if you have a strict slackness for some feasible problem, you can actually show that the dual variables, you don't have to go very far, like you can bound it within a particular thing. So it's all really about estimating this slackness by allocating some exploration slots, make sure the regret doesn't blow up, and once you get a good idea of S, then you can basically bound your dual variable, and then you can actually solve the problem. Okay, but if strict feasibility is not true, what do they get? They get T to the 3 by 4 for the general problem. Okay, so the regret guarantee actually becomes worse. Okay, so there are two things. One is the dual variables, if they are already in a compact space and you can prove it, you are done. But the other thing you can do is you can say, oh, I have this Slater condition that is satisfied, and therefore implicitly you are assuming some bound on the dual variable, but you may need to estimate by like devoting some exploration slots. Okay, so these are the two main tricks that were there. Okay, I'm not going into all the mathematical details. I'm just giving you a rough sketch of what the main issue is. Okay. Okay. Now, the same set of people with slightly different co-authors, almost in parallel to us, because we were just submitting and we saw this paper 1 week before, we were a bit alarmed because they actually tried to solve the case, the banded version, where the value is not revealed. I mean, the specialization of this general problem. So the general problem that I told you, here GT and FT and GT are revealed to you. They solved a banded version of this problem, and you can specialize it to our case. So it's very the closest to our work. So it is banded feedback, so it's like unknown value. However, they have a UCB framework, but if you specialize it directly to our problem without exploiting the special nature of this allocation function, pricing function, etc., then you get a regret that scales in the size of the support of your bit distribution. Okay, so if I discretize my bit distribution to like 10,000 values, my regret will be like square root 10,000 times t. Okay, so there is that issue. I mean, ideally I would like log b over here, because I know that I'm implicitly like framing a continuous distribution, I mean continuous problem into a discrete problem, right? So this is linear in the size of the bit. So this general framework is not sufficient to solve this problem, but they do actually, by switching to a UCB framework, they got rid of this later issue, right? You don't require any direct or indirect bound on the dual variable. In fact, our ROS constraint does not permit anything like that. I mean, it need not be strictly feasible at all. Okay, so that's the main issue. I also want to point out that after we submitted the paper, we got to know of this paper by Sinha and Rahul Vazee from TIFR. It's related but not the same problem, because they were not solving the banded version of our problem. So if you look at online convex optimization with adversarial constraints, it's a related problem where you, in our case, you will just give the full bit distribution, right? And then you will get the value for that, for example. But we don't have the luxury. We can only pick one bit from a distribution. So it's a banded version of this problem. So they establish a regret bound, which is again scaling is in the diameter of the action set times root t. So there is this particular issue. Again, all these papers are considering a more general problem. They are not exploiting any specific structure of the auto bidding problem, right? So there is nothing wrong with these papers. They are absolutely fantastic results. In fact, very difficult to get them if you think about them. But it's just that for our problem, you have additional properties that we will exploit. Okay. So this is the setting of the problem. I haven't yet told you what the solution is, right? So I have about 20 minutes. So what do we promise? Okay. So we utilize the special structure of the auto bidding problem, specifically just the monotonicity in allocation and pricing function. Okay. If you bid more, chances that your winning is more, and you will have to pay more because you're bidding more, right? So that's the only special structure we exploit. We do not need truthful auctions, can be anything, doesn't matter, but the stochasticity has to be satisfied. But there is no non-trivial Slater parameter or anything, because the ROS constraint anyway in some cases can be shown to be not strictly feasible. And the most important thing I said last, the logarithmic scaling in the support size of the bit distribution, that we actually get. Okay, but we also get some other parameter, and I'll talk about it. Okay, so I'm just recalling the problem for all of you. So this is VT times the allocation. This is the money you made, and this is the money you spent. ROS technically is 1, and you want it to be profitable, and you want to satisfy the budget constraint, right? Okay, so what's our approach? Well, it's also a UCB framework, so there is no brownie points for that. So what we are going to do is we'll start with the empirical estimates of whatever we see. Okay, so you have the allocation function. You can actually see this. If you're not allocated, it's going to be 0. If you're allocated, it's going to be 1. And then you again get an average of this for all time t. But what's interesting is that this empirical estimator is a bit different, because you have to win enough number of times in order for your estimator to actually concentrate, right? So it depends on how many times you actually win. So it's not by t, so it's very important. But we nevertheless form this empirical estimate. Okay, so what we can actually show, so what we actually do is construct these confidence bounds. Okay, what's important is that we know that xt and qt are monotonic. So implicitly consider a space of monotonic functions in B such that they are very close to this up to this fudge factors, confidence factors. So just UCB is just that I'm restricting the space. Turns out this was very useful in our analysis. Just this definition was very useful in our analysis. Okay, and this is obviously the confidence interval. Here again, all these are true with very high probability. So that we know, right, from just simple concentration theorems. Okay, so what is our algorithm? I'm first going to tell you a very bad algorithm in terms of complexity, but regret is guaranteed. Then I'm going to tell you how we make this efficient and some other challenges we faced during our regret analysis. Okay, so what you do is now you have a confidence set for all your parameters. For x, q, and v, you have a confidence set around something, right? So then what you basically do around your empirical estimate, all of them are around your empirical estimate. So what you do is you have a class of LPs, find the LP that would actually give you the maximum reward finally. Just pick that LP, play that LP, and then you will get the bit distribution, sample one bit from that distribution. Okay, so that's our algorithm. Very bad one because this is not even convex. So this space is a very crazy space because I'm talking about space of monotonic functions in B, not even continuous, but which are very close to the empirical estimates that you see. So it's just like okay, if you could form this, then this is the algorithm that we play. This is our algorithm actually. So the above problem is definitely non-convex, not even tractable. So I said a big story about Slater condition and so on, but then I ended up with an algorithm which is very, very complicated. So you have to do something to it, right? So this is what we are going to do. We are going to again use the properties of this LP. So if you just look at, for example, this LP, and let's say someone told you that you have an allocation function that is monotonically dominated by another, allocation function. In fact, not monotonically, just dominated by another allocation function. This gets looser, therefore the constraint is larger, therefore you should get a better reward estimate. So again, you make such similar arguments for Q and all of that, and what you end up with is that it's enough to substitute only these values to pick the LP. Okay, so I had a confidence bound for each of these x's and v's and q's and all of that, but all now I'm saying is that forget about all of them, just fix xt of b to be this, that's it, right? And you can find that all of them are monotonic in B, so that's always guaranteed. So this is the choice that would be for the optimal LP. Okay, that you can figure out from using the specific property of this, like ROS constraint and budget constraint and things like that. Okay, this is the main thing. So what happens is that you have one LP to solve now, and it's just B cube complexity. Okay, so at least it's just the same complexity as solving an LP over a support size of size B. Okay, that's what it is. Okay, what is the other challenge? This guy doesn't concentrate as fast as you want. It doesn't concentrate like in T, right? So it depends on how many times you win the bid, basically. Right, so the value concentrates at a slower rate because it can get feedback only for as long as it wins. It's a very yes.
Yeah, so if I do primer Willis and dual ascent, the complexity would be simpler, right?
Yes, they are very efficient.
They're very efficient.
They are very efficient. The only issue is the regret bound thing when value is not known.
So it's like t power 3 by 4 versus square root t versus in comparison to the complexities.
No, that is a regret one. I am talking about computational complexity of picking.
I'm just saying that at extra computation you get square root t regret, I believe. Yeah. They had t power 3 by 4 in your.
Yes.
So it's like, yeah, if I lose in regret, I have an efficient
algorithm.
algorithm.
I have efficient algorithm. Correct.
Okay.
That is true.
Yeah. But a stupid question is, can I solve this LP also using some kind of a gradient descent type thing?
Yeah, I mean, I'm assuming here what we are assuming is that you just give it to the simplex algorithm.
Yeah, that's B cube, so that's the reason why I'm asking, like approximately solving this.
No, when I say B cube, I mean the SDP version, right? Like because simplex doesn't converge in polynomial time.
Okay, anyway, thanks.
Yeah. So I'm just saying that it's LP complexity per time step. That's all I'm trying to say, right? Okay, so sorry, I went back a bit far. So what we again do is exploit again the monotonicity properties It is very surprising that just monotonicity of these things give rise to all these changes that you want to make to this algorithm, and the specific structure of the LP to basically show that for larger t, nt becomes effectively linear in t. Sorry, this must be small t. Sorry about that. This is linear in t at some rate. Okay. So what is that rate? That will actually come in the regret bound. So effectively it is linear in t. So you just literally have 1 over t times some factor. That's really what it is. Okay. So as you can see, what that rate is this. So if you had a concentration in t, you don't need this. You just have log b t root t. That's it. We get the regret bound, and you get the same thing for the constraint violation and this and so on, right? So the intuition is very simple. So you have an estimate that is really close to the true one, and it is optimistic from a reward point of view, right? So the reward regret must be like smaller than and the true parameters are in the confidence sets. I have made sure of that. Therefore, it should be possible to derive the regret bound. The only issue is the VT is not concentrating faster, right? So you pay for that over here. So what is this factor? Look at your LP. If I won all the time, what is the reward that you will get? V bar times t, right? But you are not going to win all the time, even if you solve the true LP. There is some times you lose. So let's call that capital V or some other thing. So it is basically 1 over the average LP win rate, okay, measured in terms of value actually. So if you won all the time, there is a value you will get. If you won exactly as many times as the underlying LP with all the things known, then you will get some value. It's a ratio of that you will have to pay. Okay, this is inevitable because if the LP and your budget is so bad, like nobody is giving you money in your marketing department, there is nothing you can do about it, right? You will only win 1% of the time. Therefore, it will not concentrate faster. So intuitively, this is inevitable, but we don't have a lower bound to show that all these things are tight. Okay, that's an open problem. Okay. And I just wanted to compare with this Castiglione, Bernasconi et al. Because in one case you know the value, the other case you do not know the value. So we just simulated all of them to just check how good the UCB thing is. It is actually pretty good in practice. The fact that you're using UCB and it is stochastic, okay, it's a synthetic simulation, there's no real data over here. So the stochastic assumption has to be satisfied. But if it is, then you are actually getting very good regret compared to these, and also very good ROS and budget violations. By the way, negative is very bad. So that's what I want to say. Okay, so conclusion is the following. I said that you get log B, you get root T without any slightest condition, but then you needed 1 over the average LP win rate, right? We want to show that that is actually indeed the lower bound. We don't have lower bounds. Okay, so that's an open problem. The other thing is when you are bidding, what actually happens in a system is that every time the same set of advertisers are not in your system, right? Because opportunities are different types of users come, they type in different types of, I mean, if I'm asking for a shoe, the airline industry would not be interested in like bidding for that particular slot unless there's a very weird connection between Nike shoes and some airlines, right? So that's not going to happen. So what happens in an actual system is that it's a pretty adversarial if you think about it from a single bidder point of view. Whom you are participating with is not an IID function at all whatsoever, right? Because it's getting constrained and so on. So there is a more involved and sophisticated modeling you could do about how the PT and the XT functions are revealed to you, potentially. I'm not specifying what they are. Adversarial is a more blind shot at the problem, but maybe you can actually exploit some extra stuff about the auction, for example. So all those things are open and very, very interesting, okay? Yeah, so sorry for disappointing you. The archive preprint is arriving soon. If you just search with the same like title, you will be able to see a paper in a week or so. I really thank the organizers for inviting me and sharing this result with you. So I'll stop here, and if there are any questions.
Thank you. You're well on time.
Okay.
And I think we have more time for questions. So please go ahead.
Yes.
So I have one particular observation about the allocation and value functions, as in you assumed monotonicity, but some kind of continuity is needed, as in if there are like only steps in allocation, then you might not be getting more signals, as in your more allocations, and then it's almost like a dumb algorithm, as in the denominator will be very less. So my leap in faith is across the landscape of the literature. Earlier you wanted compactness, then you introduce laters, and then maybe some property of this, as in diameter of the manifold or entropy. In that sense, what you are doing is kind of more assumptions on the allocation functions and trying to exploit that.
The only assumption we made is monotonicity, not even continuity.
But for like fair growth of the algorithm, you need nice continuity in the allocation.
No, we don't need it. Actually, this regret result holds. So even if there is a discontinuity, it doesn't actually matter.
Yeah, but like I'm saying,
Because
if it is like just a step function or like
Sure.
that, like maybe after a long point of time, you can just get all allocations, and through
Yes, in fact, most allocations are like that.
yeah.
Yeah, so there is no, so we are not assuming any extra smoothness or continuity or differentiability apart from monotonicity, and that's enough for this particular problem.
Okay.
Because we are implicitly saying consider all monotonic functions that are within some confidence interval. We are not even specifying what it really is, but what's interesting is that some analysis of the LP constraints and so on is able to say that, oh, we can choose this monotonic function and this one for picking the best LP from my confidence set. It so happens that you can do that. Those are also discontinuous because we rely on xt. So if you look at the actual function we pick, we don't have a choice. It's this allocation function. If the expected value of this is discontinuous, when you are sampling also, you might actually see quite a lot of discontinuity in the empirical estimate also. We are not saying anything about that. So we are just saying that this is enough basically, and you can prove it. But it is true that if you assume Lipschitzness, you can actually get a stronger result definitely for the regret bound, but we have not considered that. But the problem is the way auctions are conducted, they are indeed, if you look at the allocation function, they are indeed discontinuous. Because if you look at the second price auction, it depends on the second price. You are bidding here, you won, but you're not going to pay this money, you are going to pay what someone else basically came up with. So if that doesn't exceed some particular thing, you will not be basically allocated. So there are quite a lot of things in the pricing function and the allocation function that looks discontinuous. Yes.
Maybe let's use the mic.
Can you go back to the simulation slides?
Yes.
So I'm a little confused. So you just said that you don't assume a lot, and you're comparing with these two standard algorithms, and you are beating them quite heavily.
No, that is because we are exploiting the fact that it's monotonic, the specific property of the
So
ROS.
those algorithms are applicable in the generic setup.
So they are general algorithms.
General algorithm.
That can be just directly specialized to our case, but
Okay,
they don't
okay.
exploit anything we have. For example, the simple thing is that if you apply Castiglione directly to us, because they don't assume anything more about these functions other than some very general properties,
Okay.
the regret is linear in the bit size.
I see.
So slope itself is going to be different.
Okay.
We just wanted to check if the slope is genuinely different or not.
Now also I think there is an issue with computation, right?
Yes.
So their algorithms
Yeah,
are very
yes.
fast.
Assuming LP for us, which is B cube, yes, it is true. So we are blowing up over there, but they actually have a primal dual algorithm.
Okay, thanks.
That will be order B, I believe, mostly.
Yeah.
Yes. By the way, I haven't told you what their algorithm is. It's a bit complicated. They actually do a projection step onto, so they have various constraint sets from a UCB bound, and unlike us, they don't pick like this thing. They actually intersect multiple constraint sets, and they find the one that actually is the strictest. So those operations are not very easy either. But assuming that, okay, like I'll just give it to you that, okay, it's a primal dual algorithm, it's a very simple update, then yeah, there is some difference in complexity. But none of them are like not runnable or anything of that sort. I mean, for reasonable bit distributions, we can. Yes.
Yes.
But it would, okay, just to be very clear, it would be highly desirable to have a primal dual algorithm. No doubt about that. But it's just that I don't know how to like navigate this through to avoid this later condition to get something like that. So we, by the way, we tried all these Lyapunov techniques. So the experts in Lyapunov techniques here. So I'm not the one to say. So we only tried a few things. It didn't work. We couldn't bound the dual variable. But it is possible that there's some other Lyapunov function that you use, and there's a very different dual problem that you have, and you might be able to get good rates. I'm not disputing that.
Right. So one related question. So
yes.
I mean, you just mentioned this paper by Sinha and
yes.
So the technique that you used here, so that can be directly used in their problem, right?
No, because we have a bandit problem, right? Like the thing is there. What is the actual variable that?
Yeah. So they solve the full information setting.
Yes.
In presence of adversaries.
No, it's not the full information setting. They solve the bandit setting, in the sense that the entire W of B is the parametric space. So I pick one W of B and I'll get FT of that vector.
Right.
Right. That's what they solve for. But we don't have that luxury. We have to pick only one bit. There's no thing of playing distribution. So it's the exact difference between online convex optimization and bandit online convex optimization. If they solve the bandit version of their paper, then it would directly apply to us.
Okay.
That's
Yeah, just before I forget my question. So in your regrade bound, do I have to read that average LP win rate as a constant or some function?
It is a property of, okay.
Yeah, is it like some constant times t or just absolute constant in the regrade bound? You had this average.
It depends on rho. It depends on rho and the allocation functions and things like that. So basically, it's a property of this LP. So you will get a value V here, capital V. It's literally V bar by that V.
So just eventually it's a constant which does not depend on the horizon because this is the average.
Correct.
So it has
no, but I mean the only thing is I don't know about rho, right? Your marketing department.
No, the thing is the reason why I got it confused because you have square root t divided by this average LP rate.
Yes.
So this average LP rate has nothing to do with the horizon t.
Assuming rho doesn't depend on t. I mean
okay, so that's the caveat.
Yeah, that's the caveat.
So that's the version. That's the question I was trying to figure. If there's any t dependence.
Yeah. So if I allow constant budget per time, then you are right.
Yeah.
But if I don't allow constant budget per time, I'm literally like screwing you, not even allowing you to spend the same amount of money for all the time. Then I will pay there, and that time will come.
Okay. Thanks.
Any more questions?
Sir, one doubt, sir.
Yes.
Sir, wouldn't this bandit setting be a special case of that Sinha-Waze paper? Specific?
No. So they are solving the expected version in some sense. Okay, you have to solve the bandit version. So for example, let's go back. I mean, the only thing is they take care of constraints, right? So let's go back to the unconstrained version itself. There was an online convex optimization work from 2004, very long ago, where you play a point. You have a convex function adversarially chosen, and it just gives you the value at that particular time, right? The convex function, the point that I pick is from the simplex, right? But that's not what I can play. I can only sample from the distribution, and I can play, and I can get one vector. So you have to do some important sampling to basically reduce to that problem. So in fact, if you look at Varsha Dani's paper in 2008 or 2009, they do a bandit version of that problem. So just because you have an online convex optimization solution doesn't mean that the bandit online convex optimization solution is an immediate follow-up. You have to do something more. In fact, that's where we found all these issues with primal dual algorithms. That's why we settled for the UCB.
Yes, sir. I was trying to relate maybe the lower in terms of the lower bound. If yours is a special case in some sense.
Okay.
The other thing I had in mind was that when rho is very large, yours probably would be same as the first thing that you showed, which only dealt with ROS constraints.
Okay, so they also have other parameters. I didn't show you those. All that will happen is that your value that you get from the LP will be close to V bar, the max you can get. So that average LP win rate will be close to 1. So effectively, you will get root t times log bt. That is the thing.
Thank you.
Does that answer your question?
Yes.
I guess we need to conclude here.
Yes.
And as a conclusion, let me, on the behalf of the organizers, to give a small gift. Let us make a photo.
Thank you.
Thank you very much for your very interesting talk. And I guess now we can go for lunch, right, Gugan? Maybe you want more now.
Yeah, I can.